First, we have an exam next week on Friday during class hour, and just come to the class usually the way you come at 1:30. My plan is on Friday in 2 hours do inclusion, exclusion, and stirring numbers, which is a little bit more complicated than usual permutations and combinations. Stirring numbers is something usually students don't hear beforehand. Also, formulas tend to be more complicated. So this will be one of the hardest topics in the exam. So Friday, be here if you want to do well in the exam. Friday lecture will be about something important for the exam.
Are there any sample exams?
In the past, I give sample exams. Probably will give this year too. And I usually send it with email, so I can send you before Friday. But the Friday, we'll do the last topic. That's why I've emphasized on it. After Friday, like 3:30, we'll cover everything that's in the exam. So by this end of this week, you will know exactly what is in the exam. And my plan also, on Friday or over the weekend, I send you an email with some sample exam questions from my old exams, so that you have some idea how the level of the exam is. And then on Tuesday, maybe we can solve some of these questions. Like Tuesday, we can do a review and problem solving, so that you have some exposure to problems. I actually solved a lot of questions so far. Some of them was from my old exam questions. So you have seen some solutions, some exams solutions to some questions. So it's not completely, probably will take you with surprise. I think you will find the exam very familiar. So there's nothing too much to be scared about. There's another information that I would like to say. Our lectures are being videotaped, as you know, and they are already put into web page. So the web page, to find where they are, you go to bilkent.tr. On the front page, you look at the film archive on the right-hand side. So this is the archive of the films. And then in there you have the lectures, and then you find the Department of Mathematics, undergraduate courses, Math 110. So you can find it after this. But you start with the main page and go through the film archive, which is supposed to be on the lower right hand of the web page. And we'll have about 10 or 12 lectures already being put there. So before the exam, if you want to watch one of the lectures that you missed some way, or you want to say if you're studying, this is actually great, I never thought about this, but if you're studying your lecture notes and then you get confused about something, you can go and look at the lecture exactly what I said when I was writing it. And maybe it will fill the blanks, right? You never know. So, but at the same time, next week, because it's exam week, we'll have office hours. Like you can use some of the Thursday morning, 10:30, 12:30, Friday morning, 10:30, 12:30. So I will be more available in my office for you if you want to use the office hours. Anyway, this is sort of the plan. And any questions? Anything you want to ask? Okay, so today we will sort of wrap up this topic of repeated combinations, but in some interesting binomial formula will come up. So there will be something I think you probably haven't seen before. So let me remind you what we were doing, repeated combinations. And we'll have some form of binomial theorem related to them. Okay. Recall that the number of ways to distribute an identical balls into R distinct boxes is equal to we had discussed this. I mean, if you're distributing balls into boxes, you're basically separating balls into groups of R things. But to separate them into R things, you need to use R-1 separators, like crosses. Okay? So this becomes same as all the words you can write with n plus R-1 items. And you're choosing either n of them, or you can equally say you're choosing R-1 of them. So which is equal to, this is what I like. Note that this is the number of words with n zeros and R-1 x's. So this is actually coming from the common formula, which you can write also like this. Okay, so we have n zeros and R-1 x. It's exactly one less than the boxes. But I mean, in subtle ways, this could be answered to many different questions. One of them, which I like a lot, the number of, so this is, there are many equivalent things. Formulations of this number. For example, you could talk about the number of positive integer solutions, non-negative. So integer solutions to the equation x1 plus x2 xr equals to n. This is also n choose R-1 and R-1 either way. But this is non-negative is important because this means that xi's are bigger than 0. Sometimes we play with that condition. Like instead of bigger or equal to 0, sometimes you want them to be bigger or equal to 2, bigger or equal to 3. And once you learn the inclusion-exclusion principle, you'll even play with it, but bounding it from top, like less than or equal to 5, less than or equal to 3. So there will be some variations of this. This is actually one of the good sample questions where you can remember this as the solution of. Because many questions you face, you can convert to this question very easily. So this is actually very convenient way of thinking this number. But another one we can think of is the number of to color and balls using R colors is also. Maybe you will see that either this way or this way. I mean, this you can see it that if instead of choosing colors, you're think of these colors being in boxes and you're throwing your balls, it becomes exactly the same as this question. So it's actually very reasonable to see that way. So let me illustrate how one can use this idea to calculate something, some powers. So binomial theorem. So what we will be finding actually for negative powers, and we'll use this for some other more complicated questions. So recall again that if you take the n power of 1 plus x, this is the same. This is the special case of x plus y to the n power. Right? So this becomes n choose 0, 1, n choose 1 x, n choose 2 x squared, and n choose typical term is k, and then n choose n, x to the n. So this is what we know. So we're using combinations for this, which this meant always this n factorial divided by k n minus k factorial, k factorial. So we know this binomial. We also have, now let's think about negative powers. 1 plus x to the minus 1 is 1 over 1 plus x. And many of you probably knows that this is equal to 1 minus x plus x squared minus x cubed, x to the 4 minus x to the 5. So is plus minus powers of x. So now I want to look at a little bit bigger powers. I want to look at minus n power. So what's minus n power? It's the n power of minus 1. Right? Which means n power of this sum. Which means you have to multiply it n times with itself. And if you write it, so we keep multiplying with itself. N times. You get a mess, right? You have so many terms you don't even know what's this is. But let's try to organize it a little bit. Let's try to see it. So first of all, when you multiply 1 with everything, you get 1. And then when you get 1 times this, 1 times this, you get minus x a couple of times, right? So how many times you will get minus x? I mean, you have to choose minus x here and 1 in all of the other ones. And you can do this n different ways. Because you can choose minus x here or minus x here, minus x here. So you have n different ways of getting minus x. So that's minus nx. How many different ways I can get x squared? Huh? N ways x squared. But what if I get x squared using this times this? And then 1 for the rest. So n is there, correct, but you have to have one more term. So n is for the straight x squared, and the rest is 1, 1, 1. But there's also the ones you get from minus x times minus x and 1, 1, 1, 1. How many different ways I can get minus x times minus x? And choose 2. It gets complicated. I mean, for x cubed, we can try to figure it out. And I want to get the formula for x to the k. With your help, hopefully. We have to use logic. We have to use some thinking. So how x to the k may appear? How many different ways I can get x to the k from these products? And choose 1, and choose 2. But then, I mean, how you, like even x cubed, when you, this is misleading actually. You probably shouldn't have a sum here, but interpretation of that sum. Let's look at the x cubed again. In x cubed, the way you get x cubed is either with x cubed and 1, 1, 1, which in that case you get a minus sign. Or you could get minus x times x squared, you again get minus sign. Or you could get 3 minus x's, minus x, minus x, minus x, you again minus sign. So that means this plus minus actually is probably always true. That this is plus, this is minus, and this is like something like, depending on the parity of k, something like minus 1 to the k. So forget about minuses, just ignore the minuses. How many different ways I could get x squared? Rather than just sum of combinations, what are the ways you get x cubed? I mean, you get it from minus x times 1, 1, 1, right? From this. Or you get x squared times minus 1, minus x. You get x cubed times 1. So what those things correspond to? What are those? So you get it from, so here you get 3, 3, 0, 0, 0. Or you can get 0, 3, 0, 0, 0. 0, 3, this. You get from these. Or you can get it from 2, 1, 0, 0, 0. 2, 1, 0, 0, 0. I mean, randomly you can write things. It's like 2 ones, all the 2 ones. Or you could get it 1, 1, 1s. So exactly how many different times you get x cubed? If I put the number x1, let's use something else. A1 here, A2 here, A3 here, AN here. AI represents a power that you take from this first sum. Okay, from here you get x to the AI. From here you get x to the A2, x to the A3, x to the AN. And then to get A cubed, what should this AI satisfy? Their sum should be 3. And they're always positive. So this is exactly, this is number of non-negative integers, solutions to sum of these n numbers equals 3. Because you get AI from here, a2 from here, ak from here, and their sum has to be 3 to give you x cubed. Right? So you can now know what this is. This is number of non-negative solutions to the equation a1 plus a2 plus ak an is equal to k. It's kind of backwards. We had n before, but you know how to deal with this.
K plus
Is that correct?
K plus n minus
Now we know that number. What's that number? So this number, because of all the things we discussed, this is n plus k minus 1. Choose k. It's a very nice formula we found. So what we found 1 plus x to the minus n is equal to this formal sum where you get minus 1 to the k, and here you have n plus k minus 1, choose k to the x to the k. And we can quickly check if it works for n k equals 1. For k equals 1, this is n choose 1, so it's n. So it really works on the top. Any questions? Does this make sense? If this makes sense, I'm going to go one more step and do something crazy. So we already observed that there is this sum, and its formula is that. But why not make that formula a little bit more memorable? Memorable means it will be ideal if this was minus n, choose k. There is nothing so far which will make, we haven't defined anything like minus n, choose k. But what if we can actually define it? So for positive integers, non-negative integers, n and k define. So we're going to define minus n choose k. I would just write it here. Minus 5 choose 3 I'm talking about. Which makes no sense in terms of combinatorics. You cannot choose 3 things out of 5. It makes no sense. Right? But how can I make sense to this? I can make sense to this if I repeat the formula. Remember, n choose k have this formula, but actually, originally, it is n minus 1, n minus k plus 1 divided by k factorial. So originally, it is n times n minus 1 times n minus 2. You go like k down, and then you divide by k factorial. So I can use actually this interpretation to define minus n choose k, which means I can start with minus n, go down k times. And divide by k factorial. So this is your definition. It looks crazy because you're actually going down, which means you're going up in the absolute value. So you're actually calculating this. It looks crazy, but the numbers doesn't go down. It's just negative. In the negative direction, you're going down. So actually, in absolute values, they're bigger. But this works in our favor in this way. If I put, this is like k many of them. If I take all the minuses to the front, I get something looks like this go down to this. So what I mean is, if you take the minuses to the front, you get 7 times 6 times 5. So you can take this is a big number, so you can write it first, and this is going down by 1. Is this something that reasonable? Can you write this as a combination? What's this combination-wise? It is this factorial divided by n factorial times n minus 1 factorial times k factorial. So this is actually equal to n plus k minus 1 choose k. By defining minus n, this is definition in this way, I actually was able to write this in this kind of combinatorious way, in a nice way. Which means I can now use it here. It's exactly what I needed. Minus 1 to the k and k minus 1. So now this becomes minus n choose k. So it fits perfectly to the binomial theorem. If you have power minus n, this becomes minus n choose k. It's the exact same formula. So I can now say binomial theorem holds with this infinite sum for any integer, positive or negative, doesn't matter. And in a kind of nice way, you take care of this negative power business. It's not just convenience, it's actually meaningful in the sense that it's exactly what you're doing. I mean, you're taking minus n powers. Okay, so the conclusion is binomial theorem now holds with minus power. So if you're writing 1 plus x to the minus 5, you can just say, okay, I'm going to get so the generic term will be this, and it will never finish. It will go to infinity. You can always say this is what the answer is. You just need to remember this each time you have to calculate it. So for example, this is minus 5. So some of these numbers are 9 minuses. But it just gives you a perfect way of writing exponents. I had some difficult questions involving this. Some of this you probably don't like this. This is one of the old exam problems. I don't even remember how difficult this is, but it's just one of the questions. Now, sometimes there is some things around it, involves some more calculation than just the negative powers. But just know that negative powers you can calculate. So knowing that you can calculate negative powers, I mean, you can try to multiply this 10 times with itself and finding all the x to the 6 to 8s, which some people attempted, actually. You can try. It's not that terrible, 10. But of course, why not try to use some methods, right? So the idea here is that you should be able to express this as a negative power or something, if you can. You see that x to the 5 is common, so you get x to the 5 like this. And then you have 10 power of this, right? So that means this is actually x to the 50 times this. To the power 10. Which makes it, the question reduced to finding coefficient of x to the, you need 18 more, right? So x to the 18. So you just need to find the coefficient of x to the 18. So you get 6 to 8 total. Any ideas how to do it now? You can use brute force, but I mean, it's 10 power, so can we write this as something over something? So we are trying to find x to the 18 here. So can I do some trick here? Any ideas? Everyone noticed probably it is 3, 4, it's multiples of 3, right? Can I use that somewhere? It's multiples of 3. Yeah, exactly. So you can write this as 1 u square u cube u to the 4 to the power 10 by taking u equals x cube and then find the coefficient of u to the 6. Now it's smaller now. So instead of 18, now I'm looking at u to the 6. But again, 10 times multiplying this with itself is not the most practical way. So you need to use some other ideas. Can I write this as something over something? Multiply it. 1 u minus 1. Let me do 1 minus u. Something like this. Sure. Is this what you want? Why? Because 1 minus u is this. Infinite sum. If you multiply this with u to the 5, you get u to the 5 times this. So But then if you take 1 minus u to the 5 times this, you get only the first 4 terms. Like until u to the 4. Okay? Okay, so I know this is it, but how do I find 10th power of this? Okay, so the question is, find the coefficient of u to the 6 in 1 minus u 5 to the power 1 minus u to the minus 10. That's where the minus powers are important, right? You can always find the positive powers by binomial theorem, but now you have to use the negative powers also. So can we find the negative power of this? First, let me ask, what's the positive power? Like 10th power of 1 minus u to the 5. What will be look like? It's the positive power, right? So we all know it. 1 minus 10 choose 1 u to the 5 plus 10 choose 2 u to the 10 minus and so on. So it looks like this. I put dot because I actually don't even need to know what these are, right? Because these are already bigger than u to the 6. So I'm trying to find the coefficient of u to the 6, so I don't really need to know all the expansion in the first part. What is the expansion on the other part? This one is minus u to the power, so this is going to be minus 10 choose 1. Minus 10 choose 2 u squared. So the typical term will be minus 10 choose k with this u to the k, but this is actually minus u to the k. So you get minus 1 to the k in front as well. So this comes from the minus u. Because our formulas was for 1 plus u, this is 1 minus u. Right? So you have to adjust that. So what is u to the 6th? In terms of negative powers, let's try to write it. It should be this times u to the 6th here. It should give you u to the 6th. And then this times u to the 1. Okay? So the coefficient of u to the 6th is, first you get minus 6, minus 10, 6. This is the one that you will get for this thing, this times u to the 6. And then for the second one, minus 1, 10 choose 1, times this thing, which is also minus 1, minus 10 choose 1. So this is what you will get. But with negative powers, we cannot leave them in the exams as negative permutations, okay? All the negative permutations you have to calculate. Okay, that's the rule. So this is also the way I check if you know the formulas. So if I have negative powers, what should I replace them with? You can replace them with positive ones, and that's enough. So what's n choose k in the positive way? n plus k minus 1, choose k, minus 1. Huh? n plus k minus 1, k. Okay. So now I can write these things. So this is 1. So minus 10 choose 6 will become minus 1 to the power 6 is 6. 16, 15 choose 6, right? That's not good. And here, this is 10. minus 10 to the 1. What's minus 1 to the 1? That's minus 10. So from there you get minus 100. So you need to calculate 15 choose 6 and subtract 100.
The term minus 1 to the power k is already included in minus 10 choose k, I guess.
Yes, these are minus, because it's the formulas for positive one. To make this, you have to think this as 1 plus minus u. And that this second minus comes from that. It doesn't come from the inside. Okay? Actually, they cancel each other. When you look at the minus from inside too, it cancels it. You just need to be careful and make sure you put the steps in the right way, like reductions, getting rid of the x to the 50, getting rid of the cubes, and then think about it as possibly some positive powers times negative powers. Use the binomial for positive and negatives, and then try to write it correctly. But this type of questions I like, because what will happen is that when we come to inclusion-exclusion principle, we'll start solving questions which are using inclusion-exclusion principle. And there will be an alternative way to solve them by using negative powers. So I like if you can do these things. For example, this is actually inclusion-exclusion with this minus this. And most of the inclusion-exclusions will come from this kind of powers. So there will be connection to that theory when we come. Also, I mean, negative powers, it's something you come across too many times. I mean, you need to sometimes write this infinite series with coefficients in a correct way. So it's good, handy to know a formula for them, right? Any questions? Anything you want to ask? In the exam, you can leave it like this. You can't leave it like this, but you can leave it like this. This is, you don't need to calculate this. It's just some number. There's one more question like this. I will write the question, maybe do a couple of easy first reductions, and leave the rest of it to you. I actually have also homework. Let me write the homework first. Homework due Tuesday. Is that okay? Next week, Tuesday. You can do Friday too, but Tuesday next week. Next Tuesday. So this is from this section, 1.3 and 1.4. Okay, so here's the question. The answer to this question is not an explicit number, it's a formula. So it says find a formula. It may involve sigma. For the coefficient of x to the k in the power series. The formula is a little bit more complicated than one will like, so I ask also explicitly give what the value for k equals 5. Any idea how to start this? I mean, we probably don't have enough time to finish it, but so that if you want to try at home, you can say, this is the right way to start. Can you tell how to start? We can write as two factors. How should I separate it?
3 times x minus 1 and x minus 1.
3 times x minus 1? No, it doesn't factorize. If it did, it will be easier question. It doesn't. I mean, I'm not sure it will be easier or not, but it's a different question. There are a couple of ways to solve it, but one of them treat this as u. Start with the minus powers of that. But then you have powers like, so the typical thing will be minus n choose k, 2x plus 3x squared kth power. Maybe I should use a different thing. So typical thing will be ith power of this in I. Right? So you will have many terms, which ith powers you take. You have to see how the coefficient x to the k will turn out. Because this is now x times 2 plus 3x, you can see that x to the I is in this. Then you have to expand this using the binomial theorem. You have to also keep in mind there's 2 and 3, so those powers should stay there. And then you find the coefficient. And the coefficient will have sigma sign in it because you will have many contributions coming from different summits. But when you write those contributions and sum over some of these, you write a different way, you get something reasonable. Okay, think about it, and not Friday, but Tuesday I can solve this question if you want. Okay.